Catching heuristics are optimal control policies. There are two theories that attempt to explain how a catching agent chooses actions in order to intercept a ball. The computational view holds that the agent predicts the ball trajectory and quickly runs to the interception point in order to maximize the chances of a successful catch. Such predictive computations, however, may be hard and error-prone. Therefore, it was suggested that humans rely on heuristics for deciding where and how fast to run. For instance, Chapman noticed that if an agent runs such as to keep the angle gamma constant and the tangent alpha growing linearly with time, it will successfully intercept the ball without requiring any form of prediction. On the first view, these two theories appear to be mutually exclusive. However, as we demonstrate in simulated experiments, predictions of the computational theory are in full agreement with the heuristic theory. In the upper plot, you see sample trajectories of the ball and the agent. We check the trajectories against 4 well-known heuristics and confirm that the heuristics are satisfied within the precision of human experiments. This result means that one cannot actually discriminate between the two theories based on the available experimental data because both theories predict the same behavior. That is why we propose a new experiment that can discern between the two theories, which is grounded in the observation that certain catching scenarios can only be explained by the computational theory and cannot be accounted for by the heuristics. You can see such a case in the upper plot. The agent has to turn away from the ball for a moment in order to gain momentum. Since the heuristics assume that the agent is constantly looking at the ball, they fail to explain this catch. Finally, we study the whole spectrum of behaviors between the two extremes of purely reactive heuristics and purely predictive control policies. By varying reaction time and the magnitude of noise in the model, we find out that in most cases the agent decides to continuously visually check the ball, the one turn region in the figure. When reaction time is big compared to the task duration, the agent has to rely more on prediction, towards the right in the figure, whereas when noise is big, the agent has to rely more on observations, towards the top in the figure. When noise is high and delays are big, the agent fails to intercept the ball altogether. To sum it up, in this paper, we formulate ball catching as an optimal control problem in a partially observable environment, compare results against well-established heuristics, identify a set of novel scenarios that can discriminate between the two theories of catching, and finally, present analysis of intermediate cases that involve combinations of reactive and predictive policies.